So I'll be talking about, actually to the vortices I'll get by the end, because I understood it would be a good idea to have an introduction to the topic, and actually I'll spend a significant amount of time talking about the unitary gas, which I'm not sure that all of you are familiar, probably many of you have heard, but it's a subject with a relatively short history, basically 10 years. And during the last 10 years, there's been essentially an explosion of work, both experimentally and theoretically, in this field. So 10 years ago, essentially there were no papers, and now I think probably we have hundreds every year at least talking along. I listed here my collaborators, and I used two different fonts. The reason is because I'll use material in introduction from work I've done to this fellows in particular, but when I talk about vortices and so on, there'll be mostly work done with the people above. Okay, so let me go. What will be the outline? So it will be more about the unitary gas. I'll tell you what is a unitary gas, and here I'll spend quite a bit of time. Then I'll go very quickly through density functional theory, extension to superfluid systems. So probably most of you here are condensed matter physicists, are familiar with density functional theory, but as you might know, an extension to superfluid systems, it's not so popular because there are actually two of them only, and they've been applied only sparsely so far. But in order to study the systems, one needs it because the system is superfluid. But there is a further extension of this to time-dependent phenomena, and this is what I'll concentrate on in the second part of my talk. In particular, I'll talk about a very exotic mode of excitation of superfluid systems, which is the so-called Higgs mode. And then I'll talk about vortices and how they are generated and how they behave in a unitary gas. So, why would I like to study unitary gas? One reason, and I think this is for nerds, as I say, it means hardcore theorists, not phenomenologists. It became, as I said, about 10 years ago. You see, this colleague of mine, we organized a conference in Seattle. It was called Neighborhood 10. And he issued a challenge to that, and this is the challenge, and put money, and said, whoever solves this problem is going to get a prize. And it was $300 of his money, and then another fellow put another $300, and it was a prize $600. Eventually there was a winner. And he is a nuclear theorist, mainly, and actually he thought about neutron matter. Neutron matter, especially in neutron stars, is very dilute. Neutrons interact with a very large scattering length, essentially infinite. And he said a very good model for that, it would be a system of fermions with spin 1/2, this is how neutrons are, interact with zero range, which is a very good approximation, and infinite scattering length. What are the properties of this system? Remind you, what's the scattering length and effective range? So if you have the phase shift, there is this expansion, I think it belongs to decades, so it goes 70, 80 years back. And if you know the phase shift, you can write the cross-section in this way. And you see that when A becomes infinite, delta, the phase shift, becomes pi over 2, and the cross-section becomes maximum. This is the reason this is called unitary, because it's the maximum cross-section possible. At that point, essentially, nucleons or fermions interact essentially at infinite distance from each other, even though the bare interaction is zero range. So, if the system is dilute, only S-wave interaction is pertinent, and we don't need anything else. This describes the entire problem. So the system is very simple. Now, in order to understand why this is a beautiful problem, I'll go back, you see, to essentially 100-year-old problem. So, the hydrogen atom. If you want to calculate the ground state energy of hydrogen atom, you have to express it in terms of three constants. There is nothing else there available. Electron charge, electron mass, and Planck's constant. And if you want to make out of this a quantity with dimension of energy, this is the only one. In quantum mechanics, essentially, it's only this 1/2. If you know quantum mechanics, you know that you have to calculate this number. That was essentially why quantum mechanics was invented. Otherwise, it's essentially predicted that the energy should be at that order. But if you want the exact result, it's this. Now, if we go to unitary gas, the problem we have is the following. if you have many body system with 10 particles in a volume V, mass M, h bar, and you have effective range and scattering length, this is the only quantities which you have in the problem, and you have to express the ground state energy of that system. But now you take A to infinity and R to 0, the function becomes much simpler. And now you have a function which is essentially very similar to what you would have, at least in principle, for non-interacting system. And the only quantity which has dimension of energy, which you can form, as this form here, this will be the Fermi energy, which is defined through the density of the system in the usual way, number of particles, because you expect the system to be extensive, and then there is the dimensionless quantity here. And George, at that time, and actually nobody else, knew what that number could be. Obviously, it has to be an ordered one. It cannot be bigger than 1, but in principle it could be negative or positive. If it's positive, you are dealing with a system which is a gas. If it's negative, the system will collapse. That wasn't known. And actually at that point, there were contradictory papers published. I didn't put a name because I didn't want to embarrass the people who claimed that the system, it's unstable, it will collapse.
But doesn't it depend on the sign of the attraction? I mean, what is it repulsion?
For infinite scattering lengths, you have attraction. Only you cannot have infinite scattering lengths for impulsion. So, to remind you, so if you have, it doesn't matter, you see what this potential, let's assume you have interparticle potential that has this structure, and it has to be short range, so you can have some structure, doesn't matter what it is, but this will be of the order of the effective range. And now, depending on the depth of this potential range, you might or might not have a bound state. When this bound state is exactly at 0, the scattering length is infinite. If this is below 0, A is positive. If you have a virtual state, A is negative. So essentially, this is how you form an infinite scattering length. You cannot have an infinite scattering length unless you have attraction. Okay. Makes sense? Okay. And the problem, for example, if you have 3 bosons, not 2 type of fermions, it's known for a long time, and it's called the Fingal effect. 3 of them will collapse, essentially with 0 range.
So excuse me, maybe it's a naive question, but
it's okay. It's better to ask them now.
So then it's not just a universal number, because maybe the answer will depend on the shape of that potential and.
The only physical observable.
Now, when you take R0 going, to 0.
The only physical observable are the effective range.
Right.
This is the effective range and scattering length. There is nothing else. No matter what is the shape of this potential, this is the only observable. So the final answer should depend on those quantities. And this is actually what people know in many-body theory or something like more than half a century. You see, you open any textbook on many-body theory, you see dilute matter. It's characterized by the scattering length alone. And people the work starts with Bogolyubov, Yang, Lee, Gelman, Sawada, and so on, Huang, and it's only that. Now, if you have higher densities, we start having effective range, and people know how to write those corrections. But that's for dilute matter when A is relatively small. Now, this problem is unusual because A is infinite.
Yeah,
and you cannot do perturbation here, which people have done half a century ago. Okay. And now, you see, so it's known that boson matter will be unstable, it will collapse. So the corresponding number which was there, they call this psi, will be negative. If we have 3 or more fermions, so for example, protons and neutrons, spin up, spin down, there will be 4 kinds of fermion, it will be unstable because of the Fingal effect. But if there are only 2 of them, there is no Fingal effect, at least in the 2-body system, so it's not clear whether that's stable or not. If you have only 1, you don't have 0 range interaction, because fermions at 0 range don't interact with the Pauli principle. So you need at least 2 species. So this is the fellow who won the prize, Baker, from Los Alamos. There was a second runner-up. Yes, yeah, George Baker Jr. Yeah, and he won the prize. He actually had a relatively simple approach, and but he gave the right answer. It was consistent. And actually, the ultimate proof came in 2003. Carlson, Pandey, Schmidt, and Chung. They did the full Monte Carlo calculation. And they calculated this number. It came basically to this number, 0.4. It's positive, so that means the system is stable. But they found another thing which was really surprising in a way, that this system is superfluid, has a huge pairing gap. The pairing gap is essentially half the Fermi energy. There is no other system which has such a huge pairing gap in nature. And basically at the same time, experimentally, John Thomas from Duke, created this system experimentally in a trap, and he proved that the system is stable. So now we know the system exists theoretically and experimentally. Now, so I'm going to skip it because I'm not going to spend lots of time on many details. The initial Birch problem eventually evolved in time, became the fermions in the unitary regime. So that meant the following: the scattering length is large, much larger than the interparticle distance, and at the same time, the interparticle distance is much larger than the range of the interaction. So for that reason, for example, in the unitary limit, we can take this to infinity, this to 0, and the only parameter in the problem which has a dimension will be the interparticle distance. That's the reason the problem is so special here. But in principle, we can go away from that limit and study this problem. And this is a part of an older problem, which was studied in literature, something like 30 years before. It's a so-called BCS-BEC crossover problem. But in that case, people were concerned only with the pairing channel, not with the stability of matter under these conditions. So they actually gave only a partial answer to what happens to the system if you vary the strength of the interaction and you have, for example, this deeper well or less deep well. So if you have a dilute Fermi gas in this regime, it has, in principle, a relatively complicated phase diagram. So here you have the strength of the interaction, which is parameterized by the scattering length. When the scattering length is negative, here it's 1 over scattering length. So it's negative and small, you go in this direction, you reach the BCS regime. You have very weakly interacting Fermi gas, which you know that in that case becomes superfluid. If you go in the opposite regime, when A is positive and very small, you have a bound state, and then A becomes the order of the radius of the interaction, and you have a system where you have spin up and spin down paired, form a state of very small size, and they are separated by large distances because the system is dilute. And this system is superfluid too. This is a Bose system, this is a Fermi system. But now, using techniques which are known in cold atom, you can vary this by hand using magnetic field, phasor resonance, and you can create a system of unitarity. This is what John Thomas did. And then you can change the temperature. And the question is what happens here. Here it's a difficult problem. This is a perturbative problem, this is a perturbative problem, but this is not perturbative completely. So people calculate the energy as a function of the scattering length. This is found. This is full Monte Carlo calculation, so in principle that's known. People calculated the gap as a function of the coupling constant, and they found that at the BCS limit, the gap approached the so-called Gorkov limit, which is almost the BCS, but contains the so-called, how they are called, induced interaction corrections. So there is a pre-exponential factor which is different. Essentially, it's 1/2 the 0.4 of that quarter. And these are the calculations. And if you go to the other side, you find the dimers, which is the BEC superfluid. So we know the system is superfluid on the entire scale. Now you can change another parameter, which is, so this is what was proven experimentally in 2005, that the system is indeed superfluid by observing the abricos lattice vortices. So this was an experiment made at MIT in 2005. Now you can study the system at finer temperatures, and what you find out that, for example, if you plot on this axis the temperature, and this axis you plot the energy, and the energy has this behavior. This comes from quantum Monte Carlo calculation. This is exactly a unitary regime. And there is something funny happening here. So obviously you have a change from one regime to another. Here the system behaves like being a free fermion gas, which is kind of strange because you have an infinite scattering plane. And below here it behaves very strangely, because if you try to calculate the energy as a function of temperature, you find that essentially half of the contribution comes from Bogoliubov understood phonons, and the other half of the contribution comes from the Kuba pairs, which you break up. So this is a system which is halfway between BC and BCS limit. If you have BCS limit, essentially the entire contribution will be due to breaking up pairs. If you'll be in the BC limit, it will be sound waves of the Bogoliubov Anderson modes alone. Here, essentially, they contribute half and half. So the system behaves in a funny way. You can calculate, so once you know this, essentially you can calculate the properties of the system in a real trap. So people do this experiment. And there was a measurement of that done in 2007. There were earlier measurements, but this is the most precise so far. When they measure that here, you have to pay attention to the entropy. This is a quantity which usually people don't measure. People measure other quantities, energetic quantities, but entropy is not measured. They figure out a way how to measure this. Please.
Yeah, I was wondering, I mean, you got this energy for phonons and then an energy for quasi-particles on the previous slide.
Yeah.
Just out of curiosity, that do these somehow cross at some temperature? So
yes, they do. You see, so this is only simply to try to find out the order of magnitude they would contribute essentially in this interval of temperature from here to here. Because if you'll be at very low temperatures, essentially only this one is, because it behaves like a tau law, the other one is suppressed exponentially because of the gap. So obviously but here at this temperature they kind of become comparable in magnitude numerically. You see, at very low temperatures you'll have all those. Make sense?
Yeah.
Yeah. So in that case, you see, they were able to measure that. So they measure the entropy as a function of temperature, actually of the energy. But if you take the derivative of the entropy with respect to the energy, you obtain the temperature. So this is how they measure the temperature. And these are their results. And actually the blue curve is the results of the quantum Monte Carlo calculation used to reproduce those. And you see there is essentially perfect agreement between the two. There is some disagreement, I'm not going to talk about it, but it's basically agreement. So people now understand that part too. Now there is a new experiment. This was done this year, 2010, and they measured the pressure. Here, this is the pressure. It's the quantity is related to the pressure of a thermal gas at unitarity. And here is the fugacity, which is the ratio between the chemical potential and the temperature. And you see the black points, it's experiment. The green one, it's theory. There are some fluctuations you see in both because the experiment is not perfect. Quantum Monte Carlo calculations are not perfect because of statistics and so on. But basically there is perfect agreement between the two. And if you want other type of theories, approximate, like virial theorem and so on, you see they're quite far. So you need really to go well beyond even the virial form, which basically nobody does ever anything like this. But in this case, they can be calculated. So you see this is very insufficient. You can calculate the critical temperature, and in order to do this, what one has to do is to calculate the long-range order. This is a topic which was discussed in the 50s, Penrose, and Young, and so on. So what you do, you calculate this average, so you create a pair at some point, and then you destroy the pair at another point, and then you separate the 2 points where you create the 2. If you have, in the superfluid phase, this average is non-zero. If you are in the normal phase, this average is 0. And basically you have to do this calculation and doing some magic tricks like finite scale analysis and so on. You determine the critical temperature, and as a function of the coupling constant, the critical temperature has been determined. I didn't put the experiments there, but essentially the experiments reproduce the results. And it's interesting here that theory, typically, it's always a step ahead of experiment. And they tell them what to find. And they come in very close agreement with theory. Like this. Now, this system has another interesting property, the so-called pseudo-gap phenomenon. So imagine this is a very, very simple system. You have kinetic energy as fermions is spin up, kinetic energy as fermions is spin down, and contact interaction between them, which is simply constant in front of it. It's an extremely simple system. And it has a pseudo gap. How you determine this? You calculate the Matsubara green function, and from there you extract the spectral function, and then you look at this and find out there's a function of momentum in frequency. There is, no, this is frequency, this is momentum. There is a gap below the critical temperature, at the critical temperature, but once you're above, it disappears. And if you extract the gap from this, you find out that the gap is something like half of the Fermi energy up to the critical temperature, then drops to about half the value, so it's about a quarter of the Fermi energy for some interval of temperature, and then it drops to zero. So this was also predicted by Curie in ab initio calculation, and eventually it was measured experimentally, and photoemission spectroscopy, I think in condensed matter physics you call this ARPES. Yeah, I'm not a condensed matter theorist, even though I do publish condensed matter physics B, but I think this is essentially the same technique, like photo effect. You shine a photon and you emit the particle, you measure everything and find out. And essentially they saw the pseudo gap there. Now you can find out where this pseudo gap appears, and essentially find out that pseudo gap appears only in the region unitype is slightly before that, and I'm not going to go into more details than this, tell you only this for now. So the aim of this is to give you a very quick overview of some of the properties of this system. So I'm not going to explain that in detail, simply for you to know that there is this, there is that, and so on, and then I'll go and tell you about vortices. Now, until now, I consider the system has an equal number of spin up and spin downs. Now, let's assume that we have unequal numbers. Now, if the system is superfluid, you want to form Kuba pairs. Obviously, you don't have enough females for all the boys. You have more boys than girls. And the question is, what will happen in this case? People thought of this problem, and they gave several solutions. If the difference is not very large, and the difference between the chemical potential is not very large, you basically have the same type of pairing. However, at one point, when the difference between chemical potential is exactly delta of the square root of 2, so this is now from 64, you have the so-called water flow state. However, there was another mechanism suggested a few years back, that you might have instead this phenomenon. You can deform the hemispheres, and this is a little bit unusual because this is a homogeneous system. It's not an underlying lattice which can allow you. But, so you take one system and squeeze and you make something like a football, and the other one you squish and make something like a pizza, and then in this region and this region you can have an overlap between the two, and you can have a mechanism where you pair these states and these states. Here in loft you pair those states. In this case you pair all around. So in principle, some of this can happen, or no pairing at all.
So can a system be thermomagnetic spontaneously?
That's a good question, you see, and it's a bit more complicated. So I'll tell you what's known. Okay, so you'll see it's quite complicated, even though the system is simple. So now you can try to think of this as a function of the coupling constant. So here again I have 1 over the scattering length, but I have a minus sign here. So that means that the BCS is now on the right, so it was now on the left, and here's the BC limit. So if the strength of the interaction, so this is very weak potential, well, I don't have a bound state. The interaction is weak, I'm in the BCS regime. If the interaction is large, I have a bound state, I'm in the BC regime. And at unitarity, the bound state is exactly at 0. So now, if you vary that, and at the same time you vary the chemical potential difference, what you might expect, that when the difference is relatively small, essentially nothing happens. But then on this side, you expect loft. Another question, what would be after that? You know that the window for loft is very, very narrow. You cannot have a difference in potentials very large. It's very narrow, I think 0.72 to 0.7, something like this. There is, however, something interesting. In this case, when the chemical potential difference is large enough, you can have two P-wave superfluids. And they happen in the following way. You have the spin-ups, fermions, which don't interact because the interaction is your range. But you have a little bit of spin down. So this can interact with the spin down. You generate a sound wave in the spin down component, and that shakes the other form, the other fermions. So this is this diagram here. So now you have an induced interaction like this, which could be attractive, and that leads to enough attraction to form pairing, but it will be a P-wave pairing now in both species. So you'll have a P-wave superfluid with spin up and a P-wave superfluid with spin down. And they exist because of the existence of each other. On this side, you have a situation which is very similar to electrons. Because, again, you have too many spin-ups and a few spin-downs, and you'll form pairs, but then you'll have leftovers. And then look at what happens to the leftovers. You have the leftovers spin up, they move in a sea of bosons. And these are exactly like phonons in a solid. They exchange phonons among themselves, and you'll have in this way a P-wave superfluid coexisting with the Bose superfluid on this side. Now, what happens exactly in the middle, because obviously this transition has to be kind of smooth, it's not clear. So here you have Bose ferri superfluid, here you have two ferri superfluids, and here is not clear what happened. And here you have LOF, here you don't seem to have LOF. So what happens actually at unitarity is the following. If you vary the polarization, so here's the ratio between spin down and spin up, from equal numbers to only spin ups, like this, the energy, which is again a function of density alone, because this is a unitary system, you see you don't have anything else except each bar m and density, that's it. It's given by a very simple number. And this is theory, and this is experiment. Again, they came in the same order. First theory, then experiment. And then a little bit later, defining of the theory came, and this line here showed that you have a Larkin-Ovchinnikov phase. And now you see here the window where that exists, it's extremely wide. I'll come back to that too. So in the unitary gas, it's a very good candidate for the LOF state. Yes?
The fact that the process you're saying, that's experimental data.
This green grass.
Okay, so...
And the theory, so now I have to be a little bit more careful here. If you look, you see the system is superfluid, but the superfluid system can be normal. So you can calculate the system like you forget about the pairing correlation, and then you find this curve. If you allow pairing, you have no pairing up to here, but then you'll have LOF here, and from here to here you'll have a mixed phase. So you'll have a first order transition at this point, and the system will consist into a LOF and a fully polarized system, unpolarized system. And on this side it will be polarized, but it will be normal. And at this point it's fully.
My question was going to be, is how come experimental energy is higher than the theoretical energy? What does that tell us?
No, I'm sorry, this is experiment.
Yeah, the crosses, right?
Yeah, and the theory is here.
Yeah, so theory is telling you that the energy of the system is lower.
No, they're
what
the
is-
same point. You see, here is the
Well,
theory.
you have scattered
No.
points.
Yes, it is scattered, but if you make the measurement correctly, you'll find the agreement it's within a few percent.
Okay.
You see, so the difference is about 3 to 5%. And there are errors in theory. You see, this is the theoretical error, and they're comparable with the experimental error. So at the moment, both of them have errors at the level of a few percent.
Could this suggest that the experimental system is not entirely equilibrated?
No, I don't think so. You see, because it's quite long time. Essentially, they exist in traps, this system, for the order of minutes, and the characteristic time, now I have to work it out, but it's, I think it's microseconds or so. So it's a big difference.
Was the theory a zero temperature theory or finite temperature?
In this case, the theory is zero temperature, and the system is slightly above the zero temperature, but below the critical temperature. The temperature, it's now, you see the temperature, so I have to go into too many details, you see, in order to do a proper discussion of this. But the temperature is something like halfway to the critical temperature, roughly. So this is a very rough answer. So it's a bit more subtle. So I'll leave it at that, because I'll have to spend half an hour, or maybe 20 minutes to go into all the details. You see, each of this is essentially, well, it's a serious amount of work. The problem until now, you see, even in traps, the system is quasi-homogeneous. In principle, we'd be interested in inhomogeneous systems, so for a number of reasons. And if you want to do ab initio calculation like Monte Carlo, you cannot do this unless you have few particle systems. So you have to choose a new technique in this density function theory. The problem is that one has to find the density function, and you have to extend that to finite, to a superfluid system. So now I have the feeling I have to speed up. Remind what's the density function theory. Holmberg and Kohn said there is a function of the density alone. And then Kohn and Sham said, oh, we can simplify that and write it like this. This is the so-called kinetic energy density. You see, it's gradients of the single particle orbitals squared. This is the density, and you can write it like this. So I'll leave it at that, you see, so density function. This is kind of remarkable because of the following. So let me tell you why this is important. If you have a Hamiltonian for n particles, n could be any number from 1 to infinity. If you want to determine the ground state energy, you have to solve the Schrödinger equation. So you have to find a wave function which depends on 3n variables. Forget about the spin. So let's assume that we don't have any spin because we have then components. See how many components the wave function. Let's assume it's simply scalars. See all spins at the same time. This theorem tells us that there is a one-to-one correspondence between this function of 3n variables and this function of 3 variables only. So this is a remarkable result in mathematical terms, and it's true. So if this is true, the problem to find this is much easier than the problem to find this thing. The only problem is that we have to construct this, and we don't have a procedure. However, in the case of a unitary gas, that helps, the dimensional analysis helps. There is another problem. This applies essentially for normal systems, and as I say, not everyone is normal. And in order to realize that, I've made a list here of superfluid fermionic systems, which have been studied for essentially the last century. So starting from here, but if you look at this, the critical temperature varies from essentially to 20 orders of magnitude. But the mechanism here, 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 and here, it's essentially the same. It's BCS. Here is slightly different, here is slightly different. Okay. But we're dealing with basically the same phenomenon. So how you can do this, actually take the Kohn-Sham and extend by adding the anomalous density. You have a new phase, you have an order parameter, and you can do this. There is a small technical problem which I'm going to skip over because you have an infinity there, so I'm going to go, you see what you're going to do in the case of a unitary system. What helps again is the dimensional analysis. If you write down the energy density function, it has to be a function of density alone. There is nothing else in the theory. H bar and m, they simply factor out. They come in front. And everything else has to be. And then when you think about this, you write the kinetic energy, and this is the only thing you can write, and there is a dimensionless number, and this is the only thing you can write a dimensionless number. And if you want to introduce pairing or superfluid thing, it can be introduced only in this manner because you have an infinity. It has to, that's the only way allowed in theory. So this is kind of unique up to 2 numbers. But now you know the energy per particle in infinite method, so that fixes one number. You know the pairing gap that fixes the other number. So essentially these are fixed by experiment. This is like you write down the Lagrangian for QED, you fix the electron mass, you fix the charge, and then you are free to go. So the same thing here. You fix this and that, and you're free to go. Now, once you know this, you can minimize. Interesting now, if you want to compare theory to something, and you can do the following. You can put fermions in a trap, so now this it will be an inhomogeneous system. So all this is determined for homogeneous matter. But now you want to extend this to inhomogeneous systems. And here's the results. One of them is Monte Carlo calculation, solving exactly numerically the Schrödinger equation. The other one are the density functional theory. Essentially the agreement is better than the constants which you can determine for this system. So it's below 1% agreement. So essentially we know the function. Now you can determine the gaps on the, but there is another thing which is remarkable here. In density functional theory, you don't usually determine the quasi-particle spectrum. Here it can be determined too. So this comes as a bonus, which you don't have usually in density functional theory, but you have it here.
So what are the dashed lines there?
These, if you have a BCS or Leggett-Eagles approach for this spectrum. So this is called mean field, how good it will be. You see, and this is the real spectrum. This is the Monte Carlo spectrum. This is an early Monte Carlo calculation, which was done by somebody, I never believed it, but since it was there, I decided to put it there. But the ones which I know they are correct, it's Carlson results, which are the two here. And there are slightly two different numbers. I think he did the calculation twice. He did once improved. I don't remember the difference between the two. But basically that's the difference. So one is density functional, no, one of them is density functional theory, and the red ones are Monte Carlo. So this is how they. Okay, so now to come back, you see, to this equation, you see, apply this to inhomogeneous system, what I said that you find the unitary Fermi supersonic. How does it look? The gap oscillates, but the interesting thing to think in this system is that the density oscillates strongly. So what you have here, you have the equivalent of charge density waves at the same time with the parent of the loft phase. And this is a very good thing because that was the way vortices have been observed. So in principle, you can see law in this state if you look at the density variation. And there is a very well-defined period of these oscillations. We know the magnitude of those. In principle, there is a firm prediction from the theory. Time dependent phenomena. So I'll go through this now, what I announced in the beginning. In principle, density functional theory can be extended to the time-dependent regime. And people have worked on this for many years, and there is continuous effort. You see, there is even a website. You see, you can go and to see people meet on a regular basis. And these are typically people in condensed matter field or chemistry. And essentially what you say in density functional theory is that if you want only one thing, how the exact density of the system depends on time, but no other observable, only the density, you can write down an energy density functional which you have to augment with the time derivatives, so right, the Lagrangian, and then you take the variation of those and you obtain equation of motion for the quasi-particle wave functions. Look like Bogolyubov-Lejeune equations or Hartree-Fock-Bogolyubov, but obviously you can take correlations. There is a new element here. There are currents, because obviously you're looking at things which are in motion, so besides kinetic energy and density and anomalous density, you have to introduce currents. These appear very naturally in this case. You have to impose that system is Galilean invariant, and you know at once how this appears. So Galilean invariance already tells you how the currents appear in the theory. So you're essentially done. If you know this for the ground state, you put Galilean invariance, you know the dependence on the current. And then you're done. And the rest is dimensional analysis, as I discussed before.
So what's the difference between delta and delta X? So what were those?
Oh! In principle, you can have an external period field. Not only that generates some consensus. For example, like you have a magnetic field created by an external magnet, you can bring an external superconductor, or superfluid, which interacts with your system, and this is this. So you can have a regular external field, like a trapping system or something, and then you can have this, in principle. So the theory is developed for the existence of that theory. Okay? So I'll discuss this briefly. What I have here, I have the profile of an energy of a superfluid system as a function of the gap. And you know, this is the regular Mexican hand potential. And now, what I'll try to do is the following. This is the uniform system. Ground state is here, so it's infinitely degenerate. So, you know, I have the Gonson modes running around. But I'm going to do the following. Take the system and by hand bring it somewhere here. Slowly, adiabatically. The way I'm going to do this, because in this instance you can control by hand the coupling constant, is by changing the magnetic field very, very, very slowly. And once I'm here, I'm going to bring suddenly the magnetic field to have the coupling constant, the unitary value. And I'm going to ask, what's going to happen? Now, the naive answer, it will be the following. The system will start doing this. Okay. The answer is mind-boggling. And here is the answer. So now this is a cut to this potential energy surface, so it looks like that. So what I said I will do, I'll take the system from ground state, bring it slowly here, and then release it. So we expect the system to do this. Right? If it will be only a small perturbation, you expect you see it oscillate like this, and this has been looked upon, you see, a long time ago, and you know that the excited solve on Higgs mode with a frequency which is twice the gap frequency. So what's happening in this case is the following. This is the value of the gap normalized to the ground state value. So this is the reason you have 1. I bring it very slowly, this is time, to almost 0, and then I release it. So I took the system from here, and then bring the coupling constant immediately to the value corresponding to the ground state. And this is what the system does. What's surprising here? You see a solitron-like behavior. But the other thing which is surprising, the system does the following. It starts from here, goes to here and back, here, back, here, back. It never goes on the other side. I'm going to do a slightly different experiment. I'm going to take the system from here and bring it up to here only. And then release it. This is what it does. It starts oscillating between these 2 points. Never reaches the minimum even. Not it doesn't go on the other side. It doesn't reach the minimum. These modes are very slow. In principle, they can have an infinite period. And depends how I excite this. So the frequency of these modes is much lower than the gap. It's subtle. So you can think of this like enormous oceanic waves, like tsunami, which takes a week, you see, to go up and down. The amplitude is enormous, but the frequency is very low. The system is always homogeneous. If you try to apply anything which textbooks tell you, quantum dynamics, density doesn't change because you have no gradients, you have no velocities. So this tells you that nothing happens in the system.
It's like second sound, or
Huh?
it's like second sound, or super.
No, it's not second sound, it's 0 temperature. Now, if you apply, you see, I put in quotes because one of the ideas that exists at 0 temperature. You see, so gradient is 0. This is a constant because this doesn't change in magnitude. The only thing which changes will be the phase. So that one, it will tell you that if I do this, the only thing which will change in the gap, it will be the phase, not the magnitude. So none of this will tell you anything about what really happens in the system. And I'll limit it here. You see, I'll try to go a little bit further, simply to tell you that if you do an analysis at this time, you see a thing, very interesting phenomenon. Actually, this type of thing have been studied extensively in the weak coupling limit, and in particular for the Richardson model, which is exactly soluble to attain exactly this behavior. So these are firm results. I'm going to skip over this. So what I'm going to do now, I'm going to show you a full implementation, which is three-dimensional, of this approach. So essentially what it means, so I'm going back, I'm going to solve these equations. What this dependence is fully three-dimensional, no restrictions. And then I have to solve a system of coupled equations. Now, how many sub-indices I have here? In principle, it's an infinite number. Now, if I put this in a box, each of these wave function depends on 3 coordinates. So it's a function that depends on 3 coordinates and time, and I have an infinite number of wave functions coupled to each other. So the problem is really very complicated technically, and it's basically a petaflop problem. So let me try to convince you. I have a 3-dimension box, and I'll take 100 points in this direction, 100 points in this direction, 100 points in this direction. I have totally 1 million. What's the size of the Hilbert space? It's 1 million. So what's the total size of the problem? Is the number of points times the number of functions. Right? It's 1 million times 1 million. So in this case, it's 10 to the 12th. And add the time. And add the 2 components, u and v. And they are complex. So now you understand why this becomes really, truly very difficult problem. Now, you cannot do quantum high dynamics. I showed you there are modes there which are not described like this. You cannot do Landau-Ginzburg. It's not applicable there, so you have to do that. In principle, we do this already. And this is the tool we are using. It's indeed the most powerful computer. Probably for another 3 months or so, because China will overtake us, but probably not for long. And there is a very small number here, which you might not read. This essentially has 250,000 processors, so it's really a huge machine. And the problem which is listed here, it's actually a problem we ran. So if you go to the homepage of theirs, they show you the most recent runs there. So we're able to run essentially at full capacity this problem. I'll show you some results, you see, we should think this way. So basically what we do, we solve this system of equations. So here I wrote it in a little bit more complex way because you have 2 components, spin up and spin down. But essentially you couple this with that and this with this. So you can, for unpolarized system, you can solve only 2 of these, not all 4. So this is solved. So what I'm going to do now, I'm going to show you a number of short movies to show you what's happening in this case. And simply remind that these are fully understood calculations. The movies won't be in this presentation, so you'll have to go to this website where we are. So now I'll have to show you what's going on. So let me start. What is this here? So let me this. So now, this is how I'm showing the results. First of all, I have to explain what's happening. So in this case, I took a can of a superfluid unitary gas. It looks like a Coke can. So it's cylindrical. It has 2 ends. So the system, it's axially symmetric, and translation invariant in this direction. This is the ground state of the system. Now I'm going to stick in a finger like this, adiabatically, at the same time rotating. And I'm going to rotate for some time, and then I'm going to take this out. And then I'm going to let the system evolve by itself.
Sorry, but is the finger is some external potential or some?
Correct.
Okay.
And this you can create experimentally because this is a laser beam. So you create a laser beam, you see like this, and move like this, and then you extract and take it out. Now, what do you expect to do? So this first movie, here, so I'm not going to let it run at its speed. So this is a real-time simulation of that. So let me stop it. So I'll explain it here. In this panel here, you have the potential, because this translation invariant, you have a cut. And you see here the finger. You see the beam which appears, and it rotates. This is the density of the cloud. So because I have that finger, it's going to move the density away. Here you have the magnitude of the pairing field. So essentially, where there is no matter, there is no pairing field. And here you have the phase. We'll neglect these 2. You don't pay attention to those. So now I'm going to do this with relatively small velocity. And then I'm going to take it out. What do you think will happen?
A mix of voices.
I'm doing this slowly.
Nothing.
Exactly. Nothing happens. So I'm going to let it go. But since this runs like this, so this, at this point you still see the finger there, but soon it will go off. No, at this point, not yet. You see, it is almost disappears.
So why is the color changing on the left bottom panel?
I'm sorry, so let me stop. What's the question?
Why are the colors changing if it just rotates and nothing happens?
You see, the colors are this. This
No,
means
for-
zero,
for the
zero,
face, for
and
the
this
face.
is maximum. And you're talking about this one?
No, down.
This
here,
one?
For the face.
The phase changes. This
Right.
is how the phase changes in this particular case.
But if you don't create vortices... we
No,
use
at
that
the
as-
moment you don't create word. You see the finger disappeared, it's not there anymore. So now the system is by itself.
Oh, you don't have finger, okay.
So it was there for a while, and then I took it off. Okay? And now the system is left by itself. And you see there are some waves running around and nothing else. Right? So this is what you'd expect. Now I'm going to do something else. Okay, so let me stop this. I'm going to do the same thing with a bit faster velocity. This one. And let me do this one. So the finger, you see, you barely see it here, but it's somewhere there. You can't see it, but you see that there is a, because these are diabatically introduced in. So now you see them. So let me stop the movie simply to discuss, because it's important. So you see the finger, it's here, and you look at the density. It's zero here, maximum there. So essentially all the gas, it's in front of this spoon. So this is like a shock wave. I don't know, you see, even though you see it's free, you see this gathers the entire matter, carries it around. What do you think will happen in this case? This is a very serious perturbation of the system. Well,
We don't find the things.
yeah. Okay, I'm going to speed up the movie, you see? And if you look at this, you see the following. The pairing field, it's barely there. And now the matter, it's almost concentrated around the walls. And the phase, it's a mess. And the finger, it's still there, but now it disappears. And now it's not there, the system is by itself. You see, the superfluid, the system turned normal. So this is a supercritical velocity. So it's what you'd expect. If you move inside the system too fast, you'll lose supercritical. Okay, so let me stop this. And go back. And now I'm going to show you another one, which is this one. Okay? And the difference with the previous is that the velocity of the finger now, it's somewhere in between. But is it? No, it's not playing. Sorry. And now you see things happening. You see the finger is here. You see how it gathered all the matter. The velocity of this is still supercritical. I'll discuss that in a minute. And I'll let this run to completion, you see. Now, remember, the velocity is bigger than the critical Landau velocity. Yes. You see here holes, and if you look at the phase here, so let me discuss the phase. I'm going to stop. The phase changes from -pi to pi. So if I take this point here and look at the corresponding phase and go around that, you see the phase goes from -pi to pi. It's the vortex. It's another vortex. That's all. So here you see clearly the formation of vortices. They didn't form yet a regular lattice. but I still have my external field, just disappeared. Remember, this is supercritical velocity. The system is superfluid.
So can you just rotate your system without the beam?
How?
I don't know.
This is spherically symmetric, I mean axially symmetric.
Right.
We didn't do that experiment with the, no. But now what you see, a formation of essentially perfect lattice, because you have a confined geometry. There are 13 vortices in this particular case. So you can clearly see they're singly quantized. But as I said before, the velocity is supercritical. So let me stop this and discuss that bit. And I would like to show you one more movie, which is fully three-dimensional. And let me discuss the supercritical velocity. This particular system is remarkable in another way. It has the highest critical velocity of any superfluid known to men. Maybe to aliens, there are others, but for humans, this has the highest. So it's highest critical temperature, the highest critical velocity, and so on, among other things. How you can calculate? If you have a superflow, in this particular case, it can be destroyed by exciting phonons or breaking Cooper pairs. As a function of the coupling constant, going from BCS to BEC, breaking pairs, it will lead you to this frequency, to this velocity, which obviously increases with the gap, because the gap goes from essentially zero on the BCS limit to very large in the BEC limit. At the same time, the velocity of phonons goes in this way. And these two cross basically at the unitary point. So on this side, breaking of Cooper pairs will destroy superfluidity. On this side, exciting phonons will destroy superfluidity. Here, it's basically the same, and they cross. This velocity, if you calculate using Monte Carlo data, is that one. So this is for the phonon, and this is for the Cooper pairs breaking. 13.37. The velocity with which I was stirring it was 0.6. So it's almost twice as big. Now, how that can happen? The mechanism is relatively simple. When you move like this, you increase the density of the system. Local Fermi velocity, it's higher. So the local critical velocity is higher. So in this system, unlike in the liquid, you can have higher critical velocities. So it's very peculiar system.
But doesn't it depend on the boundary conditions that you use?
This is not a boundary condition, it's a potential level.
Well, I know, but I mean, suppose it was, you know, infinite fluid or something, and you took a stick. And did-
Yeah, I can do that too, and I actually plan to do the experiment as well. But that would have to be done in slightly different geometry. So we haven't done that yet, but we are going to do that too. Actually, we want to generate vortices, ring vortices, vortice connection, reconnection, and stuff like this. And you can do a bunch of things. Yes?
So you have a highly
It's okay.
So you have a highly compressible
Well, it's
gas.
about a factor of 2 in this case.
So I'm just wondering, because in the vortex the velocity goes to infinity, well, very high in the core. Would
Yeah.
you create a hole there?
Yeah. The velocity actually it goes. You see, I don't want to lie because I computed this too. And if I remember correctly, the profile of the velocity is
Right,
like
right.
this.
So at the
Here
maximum.
it's essentially the radius of the vortex.
Correct.
Yeah.
So isn't that?
But the instability is given by long wavelength.
Oh, no.
The large
I'm
one,
asking.
not this part.
No, I'm asking a much simpler question.
Yeah.
So if just from purely hydrodynamic point of view, you have Bernoulli law, okay? So you have maximum velocity would be negative pressure there. And wouldn't that
Over here?
pressure, yeah, would that pressure be enough to create a hole in the vortex, like, you know, the density depletion?
Yes, it does.
Uh-huh.
This is what you see here.
Right,
This is what you see, actually, if you look at the density, so in these cases, you do have.
uh-huh.
So let me go back. Oh, maybe I should. But if you look carefully, you see the plots that I showed, I have the potential, I have the density, and I have the gap. So this is indeed is very large.
but in
And you have a depletion there.
So in your model,
This is how you
actually,
cannot
yeah,
observe.
in your model
It's
gap.
not a model.
No, sorry. In your theory,
I'm very-
the gap is essentially the density.
It's given by the density to the power 2/3. with the
Okay,
constant in front.
they're proportional. So
That's
okay.
So,
Then it's
it's
like
very large.
that's like a conventional vortex then.
Yes.
Okay.
so in the later times, the red part is more dense than it is at the early times after you stirred?
So we are looking at this.
Go to the end there.
Yeah, here I have density profiles.
Right.
You see, these are density profiles at different times. And look here how big are the time. This is the inverse Fermi energy. So this is really long simulation. You see, it's not short. You see, this is where the vortex. It's a depletion.
Yeah.
You see, so you see, it's about half in comparison. But you see, most of the matter now, it's around
Yeah, but
here.
that's kind of remarkable because you also create a hole in the center.
Yes, you do.
A big one.
That's correct. Yeah. You do. So this is very fast vertical motion. It's not slow. You see, the BCS limit will barely move, but here because the critical velocity logic can do it very fast. Yes.
The other critical case where you rotated really fast,
Mm-hmm.
you had normal fluid
That's correct.
all over, and you had a little.
The metal was essentially around the wall here.
There was some gap still around the edge. Or did it disappear completely?
What gap? You're talking about the pairing gap.
Yeah, the order parameter was.
No, the order parameter is 0. It went to 0. In that
It
case.
looked like it.
No, it went to 0. I'll show you after this.
Yeah.
You see, so
I was
not
just
your best.
wondering if you get a giant vortex somewhere in the when you
Yeah.
start to rotate fast enough.
You see, in this particular case, you can interpret this as a giant vortex, you see, because you see here the density is much lower than here. So, if you want a continuum limit of this, it will give you a giant vortex. But actually, this has a microstructure, which is made of vortices which are separated by a certain distance. So the density of these vortices depends on the angular velocity with which you rotate. So now, you see, so you can interpret this depending on your eye resolution. You see, if your eye resolution is low, you can say this is a giant vortex, but if it's high, then you see the microstructure.
They haven't completely merged.
That's correct. I think when they merge, you essentially lose superfluidity. Because essentially the gap is 0 here, so essentially you don't have a gap. So if you come too close.
And 13 vortices is a magic number for
No,
circular geometry.
we obtained, you see, anything from 2 to 13 so far. But actually, not quite everything. I don't think we obtained 8, but we had 7 and 9 and 5 and 3 and 4.
There's certain,
Yeah,
the ones
so-
that fit in a triangular lattice, right?
Yes, but you see, if you have 4, you cannot make a
Yeah.
triangular lattice. So this, the geometry, it's funny. So that's one limitation. Okay, so I told you about this. Maybe I'll show you one more thing, and then I'll stop. So this will take me a bit too long. So what I'm going now to show is a very similar simulation, yeah, but now done in a different way. Yeah, so, come on.
I take the opportunity to ask another question.
Sure.
Do you think you have found anything here that you couldn't have found with Ginsburg Lambda?
You cannot do Ginsburg Landau zero temperature.
Some people do.
Yes, some people do, but that's incorrect. Doesn't make any sense.
Some people put out nonlinear Schrödinger equations for and claim that they will for the interior gas.
So let me say it again. I think that's incorrect. You see, I don't think Landau Ginsburg is for zero temperature. It's for around critical temperature. Now, here, it's a simulation. It's a little bit more complex. It's in the same can, but what I've done here, I put a stick, then I put a golf ball here, and rotate them at the same time. The reason I want to break this symmetry, and then allow, you see, for excitation of the vortex. And you'll see that the vortices start oscillating like this, but then they have an interesting interaction because this is like an impurity. And I might ask, you see, what's going to do the vortex? Is it going to bind or not to bind to the impurity?
Fine.
Depends when you ask, you see. Now, so this is another thing. Then there is other thing, you see, I'll do this and then I'll take them out and let the system evolve. And obviously I have these Kelvin waves, you see, which run around the vortices. And you ask, you see, what's going to happen? You see, are they going to be like this all the time? The interesting thing is that they disappear in the system, the vortices straighten up completely, even though they were quite bended. So this is the movie, and in this case I projected only the cores of the vortices. Okay, so you see this is the position of the stick, and there's the position of the golf ball. At the moment you don't have much, but now in a second you'll see there is a vortex which is generated and it starts sticking to the ball. Then there is another one appears, okay, and there's a third one generating, and eventually there'll be 5 of them. But the last 2 appear in a very funny way because there appear 2 of them in the same position and it will split in 2. Now, if you look at their shapes, you'll see that they oscillate. So this look how curved it is. Okay.
So how strong was your ball? I mean, how do you define the ball? I mean, what is it?
Physically, you can create it with a laser.
I know, but is it?
It's an external potential which pushes away the matter.
I understand, but
It's a repulsive field.
what? I mean, how do you define the strength of that?
Oh, I took it to be bigger than the Fermi energy, so to make sure that I remove the matter from there. And this is essentially, you see by the end of the simulation, you see these almost perfect straight lines. Okay, so this is about the last thing I'll show you. So we have quite a bit of this noise. So you see, even though they're vibrating quite a bit, they're not almost perfect straight lines. So I believe after this, you see, I'll essentially conclude. Simply to tell you, see what we're able to do at the moment. So essentially, we're only at the beginning of all this, but we can do systems with 10 to 20,000 fermions, and probably can go beyond that. Very long times, fully silicon-based, no symmetry restrictions. And we can do ground state, excited states, large amplitude motions. We can have various external fields. I'm very interested in nuclear part of this. You see, I want to look at nuclear collision, nuclear fission, and so on. It's very similar. And this is very important. So I'm thinking what to do the next 10 years. See, because we are in the petaflop work now, but we are doing in less than 10 years, we're going to be in exaflop. At that point, actually, I want to extend this by making these fields stochastic that allow me to go beyond the one body density, calculate 2 body densities, and so on. So I think that would be feasible. And anyway, this is a list of properties of the anti-Fermi gas, which I tried to comment here. Thank you.
Did you have some particular reason why your potential was this kind of Coke and not the harmonic?
Oh, I did this I wanted to look at so the potential which I took, so if I'll cut the potential along the center, it looks essentially like this. So it was almost flat here, it goes up. I didn't do it harmonic oscillator because I want to see what the fluid itself wants to do without the influence of the external field. Because the external field models the density, and they have regions where density is high, it's lower, and so in principle I can do that too. But I want it simply to look like a piece of a homogeneous system. Because this is essentially a piece of homogeneous
I'm
system.
just asking because, I mean, it's of course, in those condensates they have done these rotation experiments also, and somehow then if it's in a harmonic trap, then there are these critical frequencies. I mean, like
Yes, no, in principle I can do that, but I was interested, you see, to see what happens in the infinite system, because then I define clearly the critical velocity. You see, it won't depend on the point way, and so it's essentially the same thing. So the analysis is much clearer.
Okay,
But in principle, I can go there too.
But numerically, it doesn't make a difference for you.
There is absolutely no difference. It's easy. So in principle, you can put any crazy potential you want. So there are absolutely no restrictions numerically. See, you can put, I don't know, a pretzel there. You can do a pretzel.
So then your vortices will be curved, and then you can create vortex loops, which will, annihilate in the middle.
That's one you wanted to.
Yeah, but actually I want to do something else. I want to make them oscillate so that they'll start connecting. Because essentially nobody knows how they connect.
Oh,
Especially for the
that
fermions.
but that you can do with your
Say it again.
that you can do with your, what do you call it, when you put the defect.
Yeah.
You already,
No, you can do it in a number of ways.
right.
But I think, you see, once you do it, you see, you can look at this reconnection mechanism.
Reconnection, yeah.
Because how it happens microscopically, essentially nobody studies. You know,
Actually,
all kind of theories,
people have
assumptions.
studied for superconductors, like spinning-depinning transition.
Yeah, but they're done, you see, not in microscopic level like this.
Oh, no,
They're
no,
done
no,
in
but-
London, Gisburg.
No, but phenomenology is known. What
Oh,
happens?
no, phenomenology, I agree. No, but I want to see what Schrödinger equation tells me. So that's, you see, phenomenology, you see, you have eventually to confirm, theoretically. So I want to get there.
So you pin down one vortex and have the other one crash through it? And
Yeah, actually what I'm thinking is, I'm putting a stir which has a, maybe that's not necessary, but I'm going to do all kind of experiment. To put a stir which is not a straight line, but something like this,
Yeah,
and then have
yeah.
another one,
Yeah.
and they'll create, you see, vortices which have crazy form, but then they'll evolve and cross. And eventually I can go into quantum turbulence regime to find out, you see, how that happens, and stuff like this. So in principle, what to do after this, you see, so much. I want to look at ring vortices, you see, to generate those. And then to see how they appear, when they appear, and so on.
But how long does one of these simulations take?
It's 5-10 hours.
To do the single?
What you see, you see one of this. It depends on the simulation, but it's 5-10 hours, so it's not that long. And I think we can improve on that.
And then you can get all the hours you want for a year?
Well, this year we have, you see, so the numbers you see we have there, it's simply astronomical. The quota we have this year is 40 million hours. I apply for another 100 million. And then to tell you, see, there are 8,000 hours in a year. So, so I don't know. So essentially, we do a 10-hour run. This is essentially a 5-year CPU, 5 CPU hours. That's a 5-year CPU, whatever. So it's something like this. Yes.
Yeah, but all of this you're saying now is the same qualitative physics that you could do with Grosbitevsky in a few hours on.
No, for fermions.
Yeah, yeah.
This is for fermions. You don't do
Yeah.
Grosbitevsky for fermions. I'm sorry.
Oh, okay. That's
Show me Grosbitevsky for fermions. Where it comes from?
okay, but qualitatively it's the same kind of.
No, you see, I discussed, for example, I'm sorry, you see, that Sandy wasn't here, Sandy Feather, because I talked with him partially about these results. In Bose systems, apparently there are lots of problems. I'm not an expert there, but people have problems. Do they need or don't need dissipation? Do they need or don't need roughness in order to generate vortices? And there are all kinds of problems. Here the physics is much cleaner. Okay. In order to generate vortices, you see, I'm not an expert, I might say something, you see, which is incorrect, but this is what I'm trying to quote, you see, Sandy, and he sends me on to his review of modern physics, you see, read everything is there. So it's a bit different there. You have phenomenological parameters, which you put in, and you can vary them by hand. Here there is nothing, you see, everything is clean. You see, the parameters of the function are determined from quantum Monte Carlo, they're calculated with a certain precision, the calculation is done precisely. What comes out. If it's not like this, then you have a problem. You see, so now the problem is what is the problem? But anyway.
Okay, I see your point. My question was actually going to be: do you expect some kind of beyond quantum hydrodynamics physics, like
I showed you.
Higgs mode, or?
I showed you. I showed supercritical flow. You didn't see that before. You see, this is a qualitative phenomenon. You never see that before. Have you seen superflow with twice the critical Landau velocity? Stable?
So can you make like a spherical shock wave just oscillating like this?
Then no,
Without vortices, huh?
I think you see here, if you have
No,
easy ideas.
the radial.
I can do any kind of deformation you can imagine.
Like suppose you have a little bomb which explodes in the
I
middle
can
and
do that
produces
easily.
this thing.
Anything, I can do anything. The question is what to do. So the tool is there, so in principle now you can do anything. So there are no restrictions to the tool. You see, you can put any shape you want, any deformation you want, any probe you want. And this is the
So
power.
let me ask you this then. So if you can calculate everything,
Well, not everything, you see.
okay, let's assume you can calculate everything.
Yeah.
So what about the distribution function of these quasi-particles? I mean, do they have
No,
temperature?
that's the,
You
yeah,
have
no, so
temperature,
that's a very good question.
Uh-huh.
And this, you see, it will come, you see, when I'll go here.
Uh-huh.
Because then, you see, if you have fluctuations, you see, this theory doesn't have fluctuations about quantum fluctuation, anything. In order to have that, you need quantum fluctuation, but introducing this, you see, essentially can do it. Now, whether this is feasible or not, practically, to do calculation for Fermions, because you have sign problems, I don't know it. But I'm going to spend a few years trying to do it. So then I'll be able to answer that question. At the moment, it's essentially strictly zero temperature result.
No,
You
it's
don't
zero
have
temperature in
equilibration.
terms of the outside temperature, but not in terms of the
Outside temperature. That's another problem, you see,
of-
which I have here.
of
Is
your
the following.
fermions.
I have no idea how to implement in density functional theory the silicon. At the moment, I don't know. And I know at final temperature that's there for this system. I don't know how to put it in. If the system would be like a regular
No, 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 no.
I
No, what I'm asking is much simpler thing.
Yeah.
You have zero temperature outside, then you create your non-equilibrium
Mhm.
state with the stir or
Okay.
anything. So the question is, can you quantify this state as a state with a finite temperature? It's not.
No,
it's
I
not-
don't think. No, I think
it's
this
not-
will be a non-equilibrium
Of
state.
course,
But
of
I
course.
cannot go through too much times because obviously I don't have the equilibration anymore. So I think these simulations are valid for certain lengths of time, not too long. I believe the lengths of times which I showed you is valid because actually there have been some experiments to see how fast the unitary gas equilibrates. Experimental. You see, theoretical happen. But experimental, there is experiment. And it shows that the times are the order of hundreds of thousands of units per minute. It's a bit of this. In principle, this simulation I showed you, they are still in the non-equilibrium.
So nothing, the energy actually doesn't escape your trap.
That's
right?
correct.
So when you stir, you pump.
I can pump energy only, but it stays there.
It stays there. So
That's correct.
naively I would think that the temperature of your quasi-particles.
In
is
principle,
increasing.
if I
right?
wait long enough, they should happen. That's correct. But I don't do that, and I think it's not valid to do it.
Mhm.
Yeah.
You said you would have to put the pseudo gap in. There's no way it
Pseudo gap.
sort of naturally arise.
I didn't know how to do it in the density function. It took me a while to figure out how to do pairing gap in the density function. Now how to put the pseudo gap there, I don't know.
But you would have to put it by hand.
I
You couldn't
it's
just
there.
get it out.
It's there. Yeah, so I don't know how to. So for me, that's unknown. Maybe it's easy, maybe it's difficult, but I haven't time. I didn't have time to think of it, and I don't know of anybody who does.
Because there could be vortices in that region as well.
Good question. Good question. I don't know. I don't know. I have no clue. No idea. You see, in principle, you don't have superfluidity at that point. So, should you have? I don't know. Probably not. Naively, I'd say no, but I don't know.
Questions? Peter, thank you again.
Thank you.